Okay, so we're going to use directional derivatives to solve PDEs, right? So it's a directional derivatives. Okay, so basically there is this operator known as nabla. So this one defines the gradient of a vector. Nabla is an operator. If you have a dot product, you're talking about the gradient. If you have a cross product, we are talking about the curl.
The
Curl. Something like this. The idea is this: since nabla is equal to u of xi plus u of yj plus u of zk, if you have three components. If you have a vector, let's say x, y, z, multiplied with nabla, remember this vector is in component form as xi plus yj plus zk. And this is being multiplied with nabla, which is in the form ux plus uyj plus uzk. Now, when multiplying, you have to take note that when you multiply two vectors that are in the same direction, we get 1. They are orthonormal, right? And when you multiply vectors that are in opposite direction, they are orthogonal, so we get
0.
So this is equal to I times k, which is equal to j times k, which will give us 0. So meaning that when you have x, y, z, and nabla, when you distribute x times everything here, we're going to have x, I times I will be 1, then we're going to have ux plus y times everything here, so I times j will be 0, j times j will be 1, then we're going to have y, uy. Same applies for z times k, and everything will be 0, so you have z, uz. Okay. Now, what is this telling us? What it is telling us is that the gradient, you know, the gradient is rise over run. I suppose we have two vectors. I'll give an example of two vectors, x, y, nabla. This is the same thing as the change in y over the change in x. So the change in y over the change in x is you have the y over the x. You see that? So this is the meaning. So if we have a PDE in this form, okay, we can just simply write it as the change in y over the change in x if it is homogeneous. Okay, so that is what we'll be doing. So we see directional derivatives helping us solve PDEs. Okay, so if you have a PDE like this, you write it in a directional derivative form like this. So the change in y, you equate it with y, and the change in x, you equate it with x, and you try to solve the system. So let's try that on this example. So example 1. So we have ux plus 2uy equal to 0. Okay, so this is homogeneous. We just get the components. Here there is 1, here there is 2. So we can simply say 1, 2 times nabla of u, okay, will be equal to 0. Okay, and we see that indeed when we distribute this, we're going to have this. Okay, now the change in u. Okay, the change in u has x and y. So you can say the change in u is just dx I mean dy dx, which will be equal to, so we have y and x, which is equal to the y component, which is 2, and the x component, which is 1. So this is separable.
Yeah.
So meaning that we can write dy as 2x. Okay, so integrating both sides, we're going to have y equals to 2x plus c. And that will be the solution to the PDE ux plus 2uy. This is technically an ODE. So that is the idea. We can also have functions here in front of x. As long as it is homogeneous, then we can solve it that way. Let me look for example where we have functions in front of x and y. Okay, so all these are explanations. Okay, same applies if you have let's say b, which is a function of x and y, and you have ux, okay, and you have some value here, maybe let's say k, uy. So still we can write this as x comma y. So the x component is b, which is a function of x comma y, comma the y component is k, and you write nabla of u. Okay, now u has x and y, so we are looking for the change in y with respect to x. So we just equate the y part, the y coordinate, and the b coordinate, b of x and y, and we solve the ODE. Okay, any questions on that one? Do you have any questions?
Do we need to look for the constant?
Unless you, so the constant, you only solve for the constant if you have initial conditions. That's when you can solve the constant. Okay, so the initial conditions help you solve for the constant, the initial conditions and the boundary conditions.
Okay.
Okay, so example 2, solve the PDE ux plus y uy equal to 0. Okay, so remember this has the ordinate of x and this has the coordinate of what?
1.
So you can write this as 1, the coefficient, comma y is equal to, so y nabla u equals to 0.
Yeah.
So nabla u is just the change in y over change in x, which can be written as the y ordinate y over 1. So here we can separate variables. Okay, so we have 1 over y dy is equal to dx. Okay, and we integrate both sides. Here we're going to have natural log of y equals to x plus c. So you can make y subject here by raising everything to natural log to e to the x plus c. So here we're going to have y, e and natural log will simplify to y, and this will remain as e to the x plus c, which you can write as, since this is a product, meaning that the bases were
the same.
Yeah. So e to the c. So you write y equals to, so this is just some constant. So you can say some constant e to the x, and that will be the final solution. Okay?